So lecture today, I've been hearing some questions about spec quizzes, so we'll kind of point or just kind of point out what we should be doing. So we're in week 3. You've got your intermolecular forces and physical properties, solubility and miscibility. I'll admit the solubility and miscibility one is a challenge. I still want you to go through and do that one, but that's also probably one that I'll look at by hand and could quite likely just be giving you points back for that one. Right? Again, I would rather you attempt to see if you get it nailed, because if you get it nailed, I don't have to worry about you. But if you're missing something, then I can go through and adjust after the fact. Your Newman projections, yes, will be a challenge, and we can talk through some of that. Admittedly, I forgot to grab a model kit, even though I'm pretty sure I said that I would do that. But conveniently, we've got some pieces down here. Not enough pieces, but I got some pieces. And then conformational analysis is another one that you'll probably have a beast of a time with, which is similar to Newman projections. Nope. Newman projections has, I would argue, very little to do with stereochemistry, and I'm not going to lie, this is probably going to be the worst lecture for the recording, because what we're going to try and do is play around with model kits as best I can. Red, blue, so we'll try a couple things. So the models in drawing, and then we also have a couple other specs quizzes, molecular representation and three-dimensional bond line structure. There was a Fisher quiz or specs quiz that was in week 3. One of your classmates brought it to my attention, and I somehow either maybe just read the statement that it was Fisher projections and was like, okay, we talk about Fisher projections, it's okay. But when you actually look at the Fisher projections quiz, it's not just Fisher projections, it's interpreting Fisher projections to get to something known as R and S. Very similar to E and Z, okay? But E and Z are specific to what? And even then, cis and trans is very specific to cis and trans is technically not nomenclature. When do you see cis and trans, E and Z? When would you ever use those? R and S is a different classification, so R and S it has the same rule set-ish, but different molecules. What did you say? I can draw in-plane molecules as well, and we're not going to talk about cis and trans or E and Z. Say again? Yeah, it's for alkenes. It's only looking for double bonds, okay? And in particular, alkenes. You won't see it with carbonyls. You could theoretically see it with amines, but even then, technically imines. But that's fairly rare, and that would push into second semester, and you don't have to worry about it right now. But E and Z is in particular looking at alkenes. So if we were concerned, right, and people were talking about some of the observations that you can make. Oh, I didn't open my drawing software. Open all the way up. Hopefully, oh, come on. I figured that was going to happen. Oh, came back. So if we're talking about alkenes and we draw out a structure, an alkene is our carbon-carbon double bond. Okay, that double bond means our carbon has to have at least 2 other bonds. So we're looking at a hybridization of sp2 for each of our carbons. We could address that. But what we're referencing, we're talking about E and Z and cis and trans, would be kind of the relationship between groups. So this particular structure, we could use cis and trans to evaluate. So we'd look at our A and B groups, and we could say that they were trans to each other because they're on opposite sides of that pi bond. Okay, but if we altered this and put the B group up here, we could then say they were cis. This is not a drawing that we could use E and Z for, because E and Z is a strict nomenclature system. So in the nomenclature system, what we would do is switch this up, and we'd actually have to get a little bit more specific within our system. Let's call it a CH3, H. Yeah, we'll do CH3, we'll make that a CH2, and then a CH3. We could now go through and reference, we could still use cis and trans in describing where these things are, but we wouldn't use that or shouldn't use that name, those terms to explain the name of the compound. To explain the name of the compound, we should be using E and Z. When we talk about E and Z, we're referring very specifically to the priority of our groups. So a quick rundown on assigning that, split the molecule in half, okay, and look at each half. So if I look at the left half, I've got a CH3 on the bottom and a CH2 on top. Okay, I need to assign priority. How do I assign the priority? Okay, it's based off of atomic mass, not atomic number. Okay, so we'd go through and say, well, I have a carbon versus a carbon. Is there a difference in atomic mass? No. Okay, so what do? It's a tie, so I would now move to the next atom in the line. The next atom in the line for the bottom one would be a hydrogen, right? What's the next atom in the line for the next one? A carbon. Is there a different atomic mass between carbon and hydrogen? Yes. Which one's larger? Carbon, which means the top group has the higher priority. We go over to the right-hand side. The first atom that's connected is hydrogen versus carbon. Which one has the higher priority? The carbon, so I could star that. And now to assign my E and Z, what I would do is split along the pi bond and say, where are my stars? Are they on the same side of that blue line or on opposite? Same side, and same side we refer to as Z. Okay, so if we're going to push this name all the way out, we would reference that double bond, and we would say that that double bond is specifically in the Z orientation. Okay, I accidentally brought up nomenclature in this process, so in theory we should actually process this all the way out for our nomenclature. Okay, where's our main chain? Cool, I'm going to assume silence meant that this is what you were saying your main chain was. So that main chain has how many carbons? 5, so we would call that pent. When we look at the backbone of that main chain, do we have a different hybridization other than sp3? What's the hybridization of the carbons in your alkene? sp2. So we do have a difference in hybridization, so we want to call attention to that. We call attention to that because that's an alkene functional group, so we would call this a pentene. Okay, I'm going to throw a wicked big space in this, which we'll see in a second. Okay, before we end the name of this, I don't want to put an E in yet, or at the very end, because I need to decide, are there any other higher priority functional groups? Well, are there? Nope, so I could end this by calling it an ene. Why throw in that wicked space? The ene is a functional group. As a functional group, what do I need? I need a locator. So where is it located? Well, it's clearly located at position 3, right? Because we go 1, 2, 3. Okay, we got at least a couple people saying, no, that's wrong. Okay, I'm wrong a lot. You should call it out. That's good. Okay, we should actually say it's at position 1, 2. Okay, because we want to number such that our primary functional group gets the lowest locator number possible. Okay, so where do I want to put that 2 in my name? Okay, and this is where we hit weird gray area. You can drop it in front of the pent. So you do or 2 pent dash, sorry. Thank you. 2 dash pentene. Okay, IUPAC says that's not appropriate. Everybody on the face of the planet uses that notation. Okay, so if we're going to follow IUPAC to the letter, we would actually specify that 2 right next to the ene. Okay, so we're now being crystal clear where that alkene is located. It's located at position 2. Okay, this becomes a larger issue if you have multiple functional groups. Like if I had an alcohol in there also, the all would also show up in that name, and I'd have pentene all. If I said 2-pentenol, is the 2 referring to the ene or the ol? That's why they say you want to drop the number as close to the substituent as possible, or a functional group as possible. Okay. If we continue to process, I've got something that I did not circle, or I did not circle yet, so that would be a substituent. That substituent is 1 carbon, so I would call that a meth. Because it's a substituent, I throw in the YL. Since I've already done my numbering system from right to left with my red numbers, I would say that that methyl shows up at position 3. So we could call this 3-methyl pent-2-ene. Okay. Within that system, we haven't mentioned the E and Z yet, okay? Because we could have done a different drawing. We could have created the system where we had this. I'm going to draw the shorthand on this one. Okay. And that particular case, they would be on opposite sides, our highest priority. So that would be an ene. But if we go through and evaluate the name, it's still going to be 3-methyl pent-2-ene. So I need an extra bit of nomenclature to specify this. That extra bit of nomenclature is that Z and E. Where do I put that Z and E? Right out in front. Okay. So if we're looking at that top name, okay, we're going to have weird spacing in here. Ultimately, there is no spacing. We'd have 3-methyl-2-pentene. I need that Z out in front. That Z refers to what? It refers to the alkene. Which alkene? There's only one. There doesn't have to always be just one. So what else do I need to specify? I need to specify the location of the alkene. That alkene is located at position 2. So we could call that 2Z. But now I have Z and 3 coming up. How do I differentiate those? And that adds a whole nother layer of characters. So this is where we would usually include parentheses. You throw in another dash, and you get 2Z, 3-methyl pent-2-ene. Okay. If you flip that on its head and say I want to go from the name to the structure, generally speaking, I would just draw the structure, then assign E and Z and be like, damn, I drew it wrong, and just flip it. Okay, make sense-ish? So that's the point of E and Z, is nomenclature, and how we do it is based off of atomic mass. Nope, that's empty. So the dashes typically are between numbers and letters, okay, as a general, let's go with an estimated rule. Okay, so there shouldn't be a space there either. Okay, I can't make the statement that there's never spaces, because there are cases where you get spaces, but for the most part, there are no spaces in your names. Okay, they all run together. So that's E and Z. So the accident that I made with the Fisher projections is now a new way to look at a structure. So if we look at the structure we've got up here, we're effectively looking at it from the side, so we can see all the atoms. But do you have to look at the structure from the side? No. Okay, so if we looked at, okay, again, sucks for people that aren't here. Erase everything. Why? Finger only works when I don't want it to. If I looked at a structure from the side, say, let's do this guy, right here, and I was to draw that out, okay, how would I draw that? How would you draw it? Entirely flip it on its head, draw it. Draw that structure as you see it, which is going to be a challenge potentially if you're really careful about how we're referencing this. But draw this molecule as you see it. If you're the person going through and doing this, that I'm sort of attempting to demonstrate on the board, knock it off. Okay, we're not that artistic. Go the simple artistic systems that we've already established. In theory, you should have something like I drew up here. Okay? You may have not known what to represent the red or the blue ball as. If you did a bunch of model experience in the past, maybe you knew what those were. Okay. Typically, red stands for oxygen and blue stands for nitrogen. In this particular case, we aren't trying to say that it's any one particular atom because we don't want to mess with octets. All we're trying to do is use that as a labeling system. So what we're doing is looking at the structure from the side. Does my drawing actually reflect everything that's in this model? No? What's wrong with it? What? You could very well be right, but I don't know how your words can go with it. We'll manipulate that in just a second. Okay. If we look at our drawing, we're missing octets, right? Is the model missing octets? No, the model actually has, well, except for red and blue. Ignore red and blue. Okay. The model has the octets around our carbons. So what could we do? Fix our drawing. Let's fix our drawing so that we could actually represent those extra pieces of information. So if we went through and did that, I don't know what color I'm in. This white ball is where? So remember, the red, black, and blue are all in the plane of our paper. So where's the white ball? It's coming towards you. How do we represent coming towards you? Wedge. Is it coming towards you up above the carbons or down below the carbons? Below the carbons, which means when we draw it, we should draw it down below. And we could go through and call that white. I'm happy with that. Okay. And then we could show where my hand is holding. There's the plane of the paper. Where my hand is holding, is that in front, in back, or in the plane of the paper? It's in the back. How do we represent the back? Okay, a dash. So we can throw in our dash. Okay. For lack of a better descriptor there, I'm going to use E for empty. I think that's okay, as long as everybody's okay with that. Okay, we go over to the other side. Okay, where I'm pointing now is it's E. Where is it aimed? It's aimed up, like in the plane of the paper up. It's coming out towards you and up. So it should be out here. There's our E. Okay, and then we've got the white atom in the back, and we could go through and we could do it here. That was a little too sloppy, even for me. And we could do this. Okay. Just for the sake of argument, I'm going to draw it real fast, just for the part that I actually care about. Is that equally valid? So just the right-hand side of the molecule. It's a tough question. Okay, so if we look at, we'll call it the pretty structure that has everything specified. We have the white atom kind of to the inside of where E is, right? Right? So there it is. Everybody see that? White atom kind of to the inside of where the E atom is. More or less? Really? Is it to the inside? Is it to the inside? Now it's to the outside. Did you see what I did? Magic. Subtle change in your viewpoint on that orientation drastically changes where you would draw it here, effectively saying that those are fine. Either representation is okay. Okay? So, does that mean this is okay? Did it matter where I drew the white? We just drew our primary example. Then I had a second one that I erased. We said that didn't matter. Does this matter? Can I draw that white dash bond wherever I want? That's a challenging question. Okay? That's a challenging question that SmartWork will very irritatingly tell you you're wrong. Okay, so you gotta be real careful with how you draw these. Okay, for that white atom to be below the carbon, what has to happen? I have to do a whole rotation. Is this the plane of my paper anymore? No, we're talking about a massive shift in our interpretation of that structure. Okay? There is no physical way the drawing that I have on the right is valid. That cannot exist in reality. And because it cannot exist in reality, it is wrong. So I better make darn sure that I never draw a structure that does that, because it's going to screw up my ability to interpret. Interpret what? Okay? Interpret R and S that you don't know about yet. It's going to screw up my ability to interpret chirality. Again, you haven't heard about yet. So we really have to lock in to where our configurations are at and ensure that we're very meticulous about where those atoms are located relative to each other, and we don't start getting sloppy with our drawings. Kind of, sort of? Okay? Because we're going to show an example in a second that you'll be like, oh, yeah, you screwed that up, Mike, you can't do that. And then we'll, of course, show why you can. So this is bad. So we can't do this. So if we're going to draw a tetrahedral carbon, how should we draw it? You need two solid lines, and I'm going to do it slightly different. I need two solid lines. What shape does that make? A V. And then I need a wedge and a dash, which makes an upside down V, right? And those V's need to point at each other. Okay? As long as that is true, I'm good. But I can't do things like this because now I don't have those V's. Does that kind of make sense? So we got to be real careful with our orientations to make sure that we're drawing things correctly when we deal with our tetrahedral carbons. Okay? Which sets us up with the next question. Could I have a carbon drawn like this? Okay. And this gets weird. You're like, well, I don't have any V's, right? Okay. And if I had V's, didn't I need two solids and one wedge and one dash? Well, I don't have any solids, so what the hell's going on with this? Okay. Does this actually exist? Yeah. Take a look at this carbon right here, what I'm pointing at. Where are these two bonds? They're reaching out towards you, right? Those would be wedges. Where's the carbon in the blue atom? Heading backwards, both above and below, but heading backwards. That is a valid way to draw it. Okay? How often do we draw it like that? Not very often. Why? So one option, there's very few atoms in the plane. If there's very few atoms in the plane, I have to specify directionality for every single one of those bonds. That gets tedious real flippin' fast. Okay? So what we try to do is maximize as much as possible our atoms in the plane. Okay? That allows our drawing to look prettier and easier to manipulate. Not only do we try and maximize the atoms in the plane, we also try to max them as much as possible on the left to right axis. Why? How do we type? Do we type top down? Okay, and for people saying yes, if I was to write my name on the page, how would I write my name? And this is now a spelling test. Okay, I would write M followed by I. Do I write top to bottom? No, how do we write? I write, that's an eraser still, left to right. Which means when we're trying to draw our structures, we try to put as many possible atoms in the left-right direction, because it helps follow our natural flow, at least for English speakers. And I'm sure other languages too. What is it, Japanese that isn't left-right all the time? Japanese is up and down. So there are other languages and other cultures that shift that. And I honestly don't know what happens when you shift to organic in those scenarios. Okay? Someone should visit Japan and come back and tell me. Okay? So we've got our drawing, we've got our representation. And we run into this scenario where we could look at different viewpoints on it. Okay, so in those different viewpoints, are there other things that we could consider? So we're looking at it from the side, right? Okay, so this would be what we would look like our normal line angles. Okay, but are there other ways to look at this? Yeah, we talked about one where we could turn it where this atom, those are wedged coming at you and these are dashed going away. Okay, but if I did that, what's happening with this atom? Well, now this one's all sorts of goofy. Okay, and I get all sorts of weird results. Okay, so somebody with really complex structures went through and said, but if I look at this atom and draw it out with all the wedges and dashes like we liked, the ugly way, and then I turn the molecule, and I now look at this atom, I could turn that so that now those are all in the same configuration. And they could continue to do this all the way through with their big, long, nasty structures. What are their big, long, nasty structures? Carbohydrates. Okay. If you look at carbohydrates, they've got lots of different stereochemistry. We haven't used the word stereochemistry. Lots of different sp3 carbon atoms. It gets complex where all the groups are going. And so someone tried to go through and simplify that system. And the approach of simplifying that system, okay, they created a new way to represent our molecules. So we could go through and use this gross notation, but we're like, this is so gross. I don't want to use this gross notation all the time. Okay, because we're now talking about doing this rotation of the thing all the way around. But if I go through and say, this is called Bob's format, okay, because I know I'm in Bob's format, I can now go through and, that's an arrow. I could simplify it, where everything on that vertical axis is by definition aimed away from me, and everything on the horizontal axis is by definition aimed at me. And because that is now part of the definition of Bob's drawing, I don't have to draw them all. And so for things like carbohydrates, where we've got lots of sp3 atoms and we've got all these things floating around, we don't want to bother to draw all the wedges and dashes. I acknowledge that. Okay? But at the same time, that removes a lot of our understanding of the three-dimensional reality of those molecules, okay? And it makes it harder to manipulate. Okay? Except the people that are looking at these models don't care about three-dimensional representations because they're biochemists. Okay? And nothing necessarily against biochemists. Okay? But their focus is on different aspects, and so they come up with ways to delete information from their purview because they don't want to have to worry about it. Okay? Who did this? It's not Bob. Actually, I don't know what his first name is. Maybe it is. Okay? Fisher. Okay? So these are known as Fisher projections. Fisher projections have a couple rule sets associated with them that sometimes are really strictly adhered to and sometimes are not. Okay? The really strictly adhered to rule, everything on the vertical axis is always aimed away from you. Everything on the horizontal axis is always aimed at you. Oh, please say there was a chain in here. I thought I saw a chain. Did I break? Here, we'll do this. Different model kit. Okay, so we got a goofy, nasty molecule. We could look at all those pieces from the side. Okay, for the people at home, 1, 2, 3, 4, 5, 6. We're looking at just a hexane structure. Okay, and if I want to now convert this into a Fisher projection, what I want to do is pick a carbon. Okay, admittedly, I was going to pick the bottom carbon. We should pick the top. Okay, I'm going to take that top carbon, and I'm going to turn my viewpoint. So right, left to right, and now what do? Oh, Japanese culture. Maybe, I don't think he was Japanese. Okay, take a look at that first carbon, and I want to make sure anything on that vertical axis is aimed away from me. So we take a look at those bonds. Are they aimed away from you? Where my fingers are holding. Yeah. These two on the horizontal axis are aimed at you. So that's exactly what we want. Okay. And then said, okay, well, that's the first one. Now I got to go to the next carbon. Are those bonds aimed away from you? No. So what do you have to do? Everybody see what I just did? Just a bond rotation. Am I allowed to rotate sigma bonds? Yeah. Why? The orbital overlap doesn't change, so sigma bond rotation is perfectly acceptable. Why does that look weird to me? Okay, now you go to the next one. Are those bonds aimed away from you? Where my finger is, my hand. Those bonds are aimed away from you? No, they're aimed at you, so what do you got to do? Are they aimed away from you now? Yeah, so now you go to the next one. Nope. Now you go to the next one. Nope. Rotate for me. Ooh, that one's a tight one. Okay. And we just kind of continue that through the chain. Okay. And so anytime I now rotate along, note what happens. Every single one of those vertical axes, bonds, will be aimed away from you whenever I'm looking at it, and all the sides will be aimed at you. Legit? Okay. What's the neat thing about the Fisher projection is that if I do all of that, what happens when I now turn it and look at it from the side? It's a ring. Do we have any biochemists? And now that I've ripped on biologists so much, no, I don't know anything about biology. Anybody know anything about biology? Maybe help me out a little bit. Carbohydrates are sugars. What shape are they? When did Fisher use this? Primarily for carbohydrates. And so what he noted was that when you look at the straight chain carbohydrate, okay, you can see all the wedges and dashes, you can get that three-dimensional reality, but most sugars, at least in their storage state, are rings. And so when you did that rotation, well, dang, that sets it up where it's right into that ring shape. Okay? But this now changes my relative orientation of where those different atoms are. That can confuse things and it can manipulate things a little bit. Okay? So when we're talking about a Fisher, always on the vertical axis, dashes. Always on the horizontal axis, wedges. Okay? The next rule to Fisher is sometimes adhered to and sometimes not. Your highest priority carbon in the chain is the top carbon. Okay? That's the definition for a true Fisher projection. Unfortunately, that rule isn't always adhered to because we'll draw a structure where we want you to understand where all the things are. So we're having you interpret something that looks like a Fisher projection, but it isn't because we turned it upside down. But if I turn this structure upside down, are all the bonds still aimed away from you on the vertical axis? Yeah, everything's still legit, it still matches. It just doesn't fit the formal role of a Fisher projection. Okay, so be aware that that can mess with you. That becomes really important when you have to deal with R and S, which is what that quiz was kind of having you poke at. Okay, R and S and that Fisher quiz, for the most part, I kicked to next week because the R and S lecture is next week. It's at the end of next week. Okay, but our interpretation of Fisher is here. So we've got a Fisher representation for this. Okay, so we looked at how we could see that on an individual molecule, but now what we want to do is use yet another potential interaction behind us. Okay, right? So we got that from the side. And what did we say Fisher could do? It could do a sigma bond rotation. So I'm a sigma bond rotate, right? Does my drawing, if I redrew this, does it look the same as what I initially had up there? It's just a yes or no. You can commit. Does it look the same? Okay, so we're getting a little bit of a mixed response. Okay, so what we could do is try and draw it. The carbons are still there, right? Where's the red atom? Am I? No, I'm doing that right. From what you guys were seeing? Yeah, which is just what went through my head. But we've now fixed it, right? Are we at least all on board with that? Are we okay? Okay, there's the red atom. Oh, I like that word referencing. Okay, but we're going to have to come back to that. Okay, there's the blue. I didn't do anything to this side, so that's still my white. This is still my E. Now what happened here? On the blue side, the white is now aimed towards you and down. Okay, and the empty is now aimed away, right? Okay, so is it the same? No. So how we've drawn it does look different, okay, which is going to introduce kind of a concept. Does that mean the molecules are different? Okay, and that's a really challenging one. We're drawing it differently, and yet it's the same molecule. Okay, this is the annoying example where I'm like, what's my name? Mike, and then I turn around and you all say, Mike. Okay, all you did was turn it. That's not changing the identity of the molecule, but our drawing inherently looks different. Are you responsible for knowing that they're the same? Yeah, it does kind of suck. But yes, you're responsible for knowing that. You're responsible for that orientation. But maybe there's an out. Does this matter? Say no? Why? Why does that not matter? Cool, you would name it the exact same, right? So clearly it doesn't matter. Okay, so here's what we're going to do. We've got our molecule, right? Okay, this is the bottom one. And now what we're going to do, as we do with most things, is we're going to change our viewpoint. Okay? More or less see what's going on? See what it looks like? Okay, when we changed our viewpoint on this? So if we're going to draw this, this would kind of suck to draw. Okay, why would it kind of suck to draw? They're all kind of hiding each other, right? Okay, so if we looked at that front carbon, all right, the one right aimed at you would be our red. Shit, is that the left or the right? So that would be here, right? I mean, correct. Okay, so cool, and then empty. And then how am I going to draw this stuff in the back? That becomes kind of hard because they're perfectly overlined, like I can't see it. Okay, so this is where we go through and what we want to do is change kind of our perspective a little bit so that it helps us to see this. So there was one suggestion that we just make it kind of shift a little bit off. So if I made it shift, that's how we got this, and I did this, it shifted a little bit off, right? Does that look obvious of what I'm trying to draw? No, I would argue, if anything, that makes it really complicated, right? Okay, because this is E2 and that's E1, and E2 is the one in back. Okay, so how can I do this? I could, oh, okay, cool. I could add some dashes and I could add a wedge. Okay, so we're adding even more information of dashes and wedges. That gets really messy really fast, right? Okay, so we want to come up with a different notation for this to simplify this. So some smart person went through and said, you know what? We're going to use reverse perspective. Okay, because the front atom would be bigger than the back atom. That's perspective, right? We're going to reverse it. We're going to make the back atom bigger than the front atom. So I'm going to start by drawing that back atom. Am I in black? Hopefully I am. Boom. There's my back atom. Where's the front atom? Yeah, it's the point in the center. Okay, so now we'll talk about the back atoms, and I'll draw a line from here slightly off. Is it easier to discern where E1 and E2 are connected? Okay, I'm not saying it's easy. I said easier. Okay, and if we now continue through, really, this is what you see? Okay, it's yeah, perspective. There's our white. And we can draw our blue back there. Everybody good? Okay, so now what do we need to do? So this is the beauty on this. Because we're in this spot, we can just say, Bob's design, I don't need to do wedges and dashes. Okay, which, if you're an unk, maybe the Bob reference will actually make more sense later on, because I think it's kind of funny. Okay, so cool. There we go. What's the other thing? How did we get here? Well, what we were talking about is, did our side view, our bond angle, matter? And I said we need to change our perspective. So we changed our perspective for one of them, so what should we do for the other? We also need to do the other one, change our perspective. So we'll go back. Side view, we're at the bottom. What do I need to do? Not turn it. Even turning it that way isn't going to change anything. I'm still looking at the bottom one. What do I need to do? I need to do a bond rotation. The blue atom needs to be aimed down, right? Okay, so cool. Now I'm in that proper viewpoint from the side angle, and now what do I do? Now I'll rotate the molecule and look at it again. Now I want to go through the same process and draw out exactly what I'm looking at. Okay. This is hard to draw one-handed, so I'm going to do one more scan here to allow you to attempt to draw it first. Okay, I gave you all the rule sets for how you can go through and draw these, so you should go through and be able to draw it on your own. Then I'm going to set this down so I can draw it out. Okay, and if it helps, just take a mental picture, right? How hard can that be? Okay, and apologies for the edges, because I will probably screw up and not show those. Aim it at you very much. Okay. Don't look, don't look. Somebody laughed, so at least one person looked. And if you're like, I don't get it, don't worry about it. The atoms in front, did we move those at all? Those were all maintained in our same configuration, but what happens now with the atoms in back? Where's the blue atom? Aim straight down, right? Okay, so then we've got our white and our E. And because I put an E2, we'll put an E2 there. Everybody got it? So that's what we're now looking at. Okay, so now back to the original question that one of you was brave enough to answer. Did it matter when I did that rotation? Okay, and one of you said, nope, doesn't matter. Looking at it now from the side view, okay, or end on, better way, do you think it matters? Discuss at your table. He's cheating. He talked to me in office hours. What'd you guys decide?
Individually, it probably doesn't matter, but in terms of interacting with other molecules, it probably does matter.
Okay. Why?
Just because if they're all, like if you connect a bunch of the same molecule together, and they're all pointing in the same way, they could potentially just overlap on itself, I guess. I'm trying to
Okay.
think of it as a
Okay.
puzzle
So
piece.
kind of like that Fisher projection that I kind of did with the model, that it all overlapped back on itself.
Right.
Interesting. Yeah. So what do we think? We think we got a class consensus. Does it matter? Okay, we don't have a class consensus. Okay, we got some people saying yes, some people saying no. Okay, what do the lines represent? What do bonds represent? Electrons. And what happens when I get electrons near electrons? They repel each other. So if I take a look at this bottom example, right? Bottom example, there it is. These electrons and the bond, if you're having a hard time seeing which electrons, I use a different maker, okay, that I'm pointing to, we can turn it from the side, right? The electrons we're talking about for the blue and the red atom. Okay, they're in the exact same plane. They may not be on top of each other per se, they're on top of each other in our drawing, okay, but they're in the same plane. So in the three-dimensional reality, they are occupying the same space, they're occupying that plane, which by definition means they want to repel. Okay, so if they repel each other, what are they going to do? Sure, do what I want. What did I just do as they repel? I rotated what? I did a sigma bond rotation. Would I continue to rotate? What happens as I continue to rotate? I run into the exact same issue, which then means it goes, well, I don't really like that, and I'm going to continue to rotate some more. Okay? And then it can overlap again. And so what's going to happen is as you go through this, you will see sections where they don't overlap and where they do overlap. Where they do overlap is now actually a higher energy state. Well, why would that matter? This is going to have to do with reactivity. And if we're going to look at our molecules and try and model their reactivity, what we want to understand something about is where are they starting? Okay? And if I look at these two structures, which of those two structures best represents where my molecule is going to start? The top one or the bottom one? The top one, because it's lower in energy. Why does that matter for me? Well, now I want to chemically react. Where those atoms are located in three-dimensional space is going to change how they interact. You're like, no, that's not possible. Really? If I reached out to shake his hand, is this a reasonable orientation? But if I hopefully doesn't reach out to shake my hand now, because that's going to be very uncomfortable for both of us. Okay? So the orientation of where those atoms are is very, very important. And so we have to understand something about where they're located. Okay? Which then means, because there is a difference in energy, what do we now need to do? Whenever we find a difference, we name it. Okay? So we now have to come up with a way to describe what we're seeing. Okay? The first person that went through and said, hey guys, there is a difference here, okay, probably gets to do what? They get to attach their name to it. And the name for this is Newman. Bob Newman? It was an Unc reference. That's fine. Okay. In any case. Okay, so cool. There we go. We're looking at Newman projections. So now we know the class. The Newman projections is now not looking at the side view, is looking end-on. Okay? And when we're looking at that end-on, we now want to be able to name the different representations between these. So what do we see? What do you see in each of these would allow you to come up with a different name? So you got them like that. Okay? That's a really, so the bonds are really close together versus really far apart. That doesn't sound very sciencey, fancy. I'd like a word, right? We want to keep this as simple as possible, right? We want to invent a word that helps to explain these. What? Okay, when we get a solar eclipse, what's happening? That was a bad example. I don't know exactly what's happening. Some things come into alignment so that we can't see some other things, right? Okay, they're overlapping. That bottom one looks like they're overlapping. So that's an eclipsed configuration in a Newman projection. The eclipsed configurations in and of themselves, I would argue, aren't super important because when we're talking about those are energy maximums. Okay? Because as I rotate, I get lower in energy. As I continue to rotate and get to another eclipsed configuration, I go higher in energy. So if I was going to look at how this transitioned with a rotation, that says rotation, trust me, and energy, these peaks are going to be my eclipsed configurations. Okay? And I could talk about how much higher or lower in energy they are, okay, if I really wanted to deal with mathematics. Do you want to deal with mathematics? Cool, you just need to know relative terms. That's all you need. Okay? What I'm going to care more about aren't those eclipsed positions. I'm actually going to care about the valleys. Because these are the places where my molecule is now going to primarily exist, quote unquote. That's where my chemical reactions are potentially going to happen. Okay, so I want a name for that. So what kind of name could I drop on that top one? This is where we encounter the term staggered. Those groups are staggered off of each other. Okay, now the staggered off of each other does have an important distinction that we need to be aware of. We'll make it a little bit more dramatic. Okay, so the blue atom now just has a bunch of extra stuff attached to it. That's all I want to do for the sake of the model. Okay, and we want to go staggered, right? So, am I staggered now? Everybody agree? Is that staggered? Sometimes it spins in my hands. Okay, I don't care necessarily about the two big black things on the top. Don't worry about those. Okay, all I care about is on the bond that I'm sighting down, that bond that has disappeared, am I staggered with all the bonds that are connected? Okay, I could continue to rotate. Higher energy, higher. Okay, a little lower energy, right? And we're at that one. Also staggered, right? Are these staggered the same? Ooh. And if they're not the same, what do we need to do? Now we need new names. Okay, why are they different? Which one would you expect to be lower in energy? The one I'm holding on to. Why? Okay, those groups are further apart. Okay, if we go back to this one, what's the potential problem? Because those are, stop spinning there. That sigma bond rotation is that clinking sound, for the sake of the microphone. Okay, that clinking sound is the groups hitting each other. That's atoms colliding. That's not particularly good. If we rotate to the other configuration, do I get that same clinking sound? For the sake of the microphone. Okay. So we want to be able to be aware and point those different systems out. Kind of make sense? Okay. So staggered splits into two categories. We're going to get the categories where our groups are as far away from each other as possible. Well, which groups? Said another way, right? When I did this, you said they were as far away from each other as possible? Really? This white ball is as far away from that empty space as possible? The red and the blue groups are. Why do I care about the red and the blue groups but not this other one? So we need to come up with a criteria to evaluate. So we could do something about higher priority. Priority, nice call, by the way. That was a lovely idea. Isn't relevant. But that was a really good idea. I liked that one. What was I doing? I was rotating. I was clinking them. How was I able to clink them? Yes, sigma bonds, and what else? Could I clink them anymore? No. What was different? I had more atoms there. You meaning the size of the group is now going to have a physical impact on this. Okay, so the size of the group is really dictating it. So why do I not care about that white atom in that empty space? Because the size of those groups are small, which is why I didn't pick colors for them. Okay, the blue and the red were the one we wanted to identify. Sorry, the red and the blue. I switched it again on you, didn't I? Damn it. Okay, the red and the blue were the ones we were calling attention to. We decided that those were the quote-unquote biggest. So when we're talking about that low energy state, we want the biggest groups to be as far away from each other as possible. And we talk about the other low energy state, but not the lowest, they're kind of close to each other. Okay? This is where if you watch the video on Newman projections, it talks about awkward descriptions, things that some people are laughing at because you watched the video. And if you didn't watch the video, okay, you'll get a little bit of a preview now. Okay, it really only helps for the male audience, but maybe the female audience is aware of what happens in male bathrooms. Okay, in male bathrooms, you've got urinals because sometimes we don't need to sit to use the bathroom, so we can just stand and pee into a hole instead of actually going into a station. Okay, but there's a male etiquette with urinals. Okay, there's multiple urinals. If you go in, you get to pick whatever urinal you want, right? But if you go in and there's somebody using a urinal, what do you have to do? You go to the farthest one away. Okay? We want to go to the farthest one away. We want the lowest energy state. Which urinal do you absolutely not use?
Unless you have to.
Yeah, you can use the one next to them. That might be a little awkward. That might be a little gauche, but you damn well don't use the same one. Okay? Because that's really high energy. That's your eclipsed configuration. Okay? That's not a good idea. Okay? I would bet women have similar protocols. You don't go to the same stall that somebody else is in, right? That's eclipsing. That's a bad idea. Okay? I don't know. I haven't been in that situation, but I would assume. Okay? And then since you're in stalls, I don't know that you need space between. Is that a thing? Do you need space? You don't care? I don't know. Maybe that's asking getting too personal. I apologize. Okay? But that's what's happening within this system. That works as a decent analogy. Eclipsed, don't pee in the same urinal. Staggered, ooh, there's a nuance. Okay? Maximize space as much as possible. And then if I don't have a choice, I can use my own urinal right next to them. Okay? But even then, that can be a little awkward. And if you break down the term gauche, what does it mean? Awkward. Okay? You're just a little too close. I stepped with. I'm sorry, Karen. Okay? That's what your Newman projections are doing, and those terms help to explain energy differences between our molecules. Okay? So you need to be able to recognize the energy differences, and this becomes the mess when it comes to the specs quiz. You have to be able to look at a side view structure and draw the Newman projection. Okay? And that takes a little bit of practice to manipulate and work with just on its own. The specs quiz will actually make it even harder, and I don't know if it was intentional or not. I would bet it was not intentional. Was I okay to erase all that? Okay, good. Okay, so we could go through and draw a quick-ish example. We'll make that wedge. Three. Yeah, we can do something like that. So we could go through and say, well, I want the Newman projection for this. So first things first, if I want a Newman projection, I need to look down a single bond. Okay? Do I have just a single bond in this structure? Okay, just one single bond? What kind of bond is this? That's a single bond. What about that? Single. So they're all single bonds. So which single bond do I look down? Because that's going to change how you would interpret it. Okay, so you've got to be really particular with what bond you're trying to look down. Okay, and the more clear you can be, the better. And that's where you get, for me, the creepy looking eye. Okay, right? Eyelashes, you know, bloodshot, and there's some veins, and it just looks monster eye. Okay, what we're doing is looking down that bond. And that helps to really put the frame of reference on a lot of things. Number one, what can you tell me about that red dot? True, it is a carbon. Continue. It's the one in front. So when I go to draw the Newman projection, that's going to be my dot in front. Okay. What could you tell me about the blue dot? That's the one in back. And if we think through the Newman projections I drew, right, because we drew some Newman projections that I conveniently deleted, we drew it like that, more or less. If I drew it like that on this Newman projection, did I do a good job? No, why not? I'm not even specifying necessarily what all those are. This gets like a weird question because it's how are we representing this? Where's the in the plane bond connected to the red carbon? That red dot Where is the in the plane bond? In the plane of my paper, where's that bond?
In between
The red and the blue dot are in the plane. Yeah, crap. They're in the plane for my paper, yes. Okay, but when I now take it and turn it to look at it Newman projection, where's the other bond that's in the plane? Okay, because if I take this, I'm going to grab that red dot and I'm going to pull it out. And if you're saying it's the wedge, okay, where's the wedge? It's right here, right? There's the wedge. Feels really awkward. Okay, and if I'm going to grab that front carbon red and I turn towards you, is that in the plane? That's off to the side. What's the in the plane atom? It's that bond. That bond is in the plane. It's shown as a solid. And where is it aimed relative to my carbon structures? Down, so I would draw it like this. Why is drawing this a bad idea? It's not oriented that way. Okay? It's all about looking at the orientation of your structure. Okay? What you're trying to do is the minimal amount of rotations as possible to be able to navigate this. Where should that wedged atom be? Let's see if I can pull this off with you all. Remember, there's that wedge one. And what happens if we turn it? It goes to the right-hand side, right? Right-hand side where? On the upper angle, right? Okay. Is that the left? Okay, good. There's our right. Okay, what group is that? That's 1, 2, 3 carbons. Okay, so I could go through and go 1, 2, oops, sorry. No, you were right. Thank you for saying that out loud. We're talking about that wedged one on the right was this, which is just that one carbon. That's a CH3. But it does remind me we need to double back to our red atom down here. What is that? That's not a CH3, that's a CH2. So I could go 1, 2, 3, right? So I get my 3 carbons. That's going to start to look really gross, isn't it? Okay, is there something else I could do to help make this look easier? What would 3 carbons be? 3 carbons would be prop. And prop begins with PRP. You can pick any notation you want. You can simplify this so that you don't have to make it as big and gross and messy. Okay? What atom's out here on the left? I didn't show anything. Keep your mouth shut. What atom is that? Right here. What atom should I be putting right there? A laser pointer would be a lot more useful. Ta-da! What atom should I put right there? Isobutyl, no. It's connected to the red dot. So I got to go back to my drawing and find my red dot. That was my front carbon. What atom is connected there? I'm starting to hear people increasingly whisper it beyond the first person, and I'm hoping the secondary people did not hear what the first person said, and they're coming up with it on their own. Okay? There has to be another bond there, right? I have to have another bond there. Why do I have to have another bond there? I have to satisfy the octet. So what's that other bond? Okay, for people saying it's a CH3, it's because I just drew that line, so back off. Let me undo. Oh, is it a CH3? It can't be a CH3, because if it was a CH3, what would you see? You would see the point referencing that there was a carbon there. There is no point there. What is there? It's a hydrogen. There's an implied hydrogen that is dashed going away from you there, which means, boom, hydrogen. What happens with the back? You could continue to draw that out. Okay, which part do you want to look at? Cool, the weird fishtail thing. What was the weird fishtail thing? Isopropyl. Okay, that fishtail thing relative to the carbon structure that we already have is located where? Straight up. Okay, it's in the plane of the paper and it's above the rest of my structure. I won't say that one out loud just because that's too funny. Okay, what else do I have? I have an ethyl. Where's that ethyl? Okay, so this is where you got to be careful. Behind versus in front is going to come from your relationship on what you're answering. Okay, the ethyl in my side view is in front coming at you. I don't care about it there. I care about it in my drawing. Where should it be in my drawing? Okay, okay, and what I just noticed is what everybody should be doing, and they haven't started doing it yet. They're starting to do like this weird thing. They aren't trying to dance. They're trying to use their hands. Or maybe they're trying to dance. Okay? They're trying to use their hands to act as a model kit. How many of you have a model kit? Because if you're looking at this being like, what the fuck are you drawing? You should probably pull out your model kit and start using that to manipulate these things. Because you're right, it is very difficult to piece these things together. And so we'll come up with ways to manipulate them. Your hands do work. They get a little bit tricky and it does look a little scary sometimes. That's why it makes sense to use the model kit. The model kit allows you to manipulate where those spaces are and figure out where they're at. Instead of trying to do a two-dimensional to three-dimensional to two-dimensional representation as we're navigating right here, in your head, which we said already was a very scary, nasty place to be, okay? Do it in front of you with the model kit. That will help you to navigate that system, and it will minimize some of the mirror issues that you're going to get, which you've been noticing maybe I've been having of like, was that on the left or the right? Because I'm looking at it from a different perspective than you, and I can never figure out which way is left and right. Okay? So if we take a look at this ethyl, which we've identified, right? This is an ethyl. It's out here. And we do the rotate. Fudge me. God damn it. Where the hell am I? Red's there. Ethyl's here, right? Now what happens? It's to the right. And to the right would be here. Okay. Thank you. Okay, we have our ethyl. What's to the left? That was awfully fast. How'd you get that? There we go. Leverage the stuff that you've already done. You've already done that. There is an implied hydrogen. Or she blows. Sorry, it sounded sea shanty stuff. Hydrogen dash going away from you. And you now have this system that now represents this structure. Okay? So cool. You spent 5 of your allotted 10 minutes to draw one Newman projection, and on top of which, you don't even have the answer. Because what does the stupid question have you go through and acknowledge? They go through and say, this is the Newman projection we're going to draw. We've got labels A, B, C, D, E is the next letter, and F. And they go through and say, I want letter A to be the CH3. Does your Newman projection show CH3 straight up? No, it does not. Which means if you use this to answer the question, you are wrong. Okay? But what do you need to do? Rotate. Okay? So if it was me, because I'm slow, okay, what I would end up doing is taking a look at my structure and saying to do this rotation, there's that CH3, I need to rotate it this way. I want this shape. There's my CH3. If I'm rotating it that way, the hydrogen rotates down there, so there's my hydrogen there. The propyl rotates there. Note, I said isopropyl, not propyl. Be careful with your labels. Okay, the isopropyl goes over there. Ethyl's there, hydrogen's there, and I now have the answer. And everybody that was drawing that out was like, cool, that was really fast. I caught up with you. There's a different trick. You ready for this? You all have the paper in front of you. For those people that actually drew out the first drawing, right? Turn the paper. I think it's 30 degrees in this case. 60? 30, 60, 60, 60 degrees. You turn it 60 degrees. Now answer the question into the specs quiz. Okay? That works for the specs quiz, but what if it's an exam? For an exam, that's why I reflex into this, because I would have a hard time doing those manipulations. Particularly because more than likely where you're drawing it is right next to the question. And so if you rotate your paper so that it comes into alignment, your answer is now in alignment, but your answer choices are now out of alignment. And so you're stuck in this weird, like, which way do I go? That's why I would always redraw it. Does redrawing it take time? Yes. Okay. But it can guarantee that I'm right. So I will spend the time to redraw it. And I will commit to that at the very beginning of the question. I know I will have to draw this a bunch, so I'm already reflexing into drawing it a whole bunch. Not this, maybe I don't need to do it, maybe I do. Draw it out. Kind of, sort of. How do we feel about Newman projections? Yeah. Better. Okay, that's good. I can accept that. What questions do you all have? Two minutes? Let's talk about some molecular orbital theory then. Yes. Yeah. Okay. I've been in some classes where they'll go like, oh, I don't want model kits on the exams. And I go, okay, so you're telling students to not use a model kit, right? Like, well, no, I want them to use them. Well, where's the incentive to use the model kit? So yes, you are absolutely allowed to use it on the exam. When it comes to the exam, since we don't have a whole lot of time, I'll mention it now. You should not come in with just pieces of model kit everywhere. Okay, particularly if you have that gray kit, because people are going to start punching you if they're coming. Okay. Okay. So instead, what you should do is build a cyclohexane, and you're like, what's cyclohexane? We haven't talked about that yet. Yeah, that's next week. Okay. It's another mess that is based on Newman projections, so you got to understand your Newman projections first. Okay, but you'll build a cyclohexane, and then you'll put two methyl groups connected to it. The methyl groups have 4 bonds, so on the remaining 3 slots on those methyl groups, you put as many different colors as you possibly can. So you want to do a Newman projection, what do? You pull off the 2 methyl groups and you connect them. Ta-da! You now have the ability to do Newman projections. You're like, but it says propyl. No, it doesn't. It says red ball. Okay, it says blue ball. Put the colors onto your map so you don't have to think about those larger groups. And as long as you have it keyed, you can do that translation to your answers much swifter. Okay, does that help? And then you'll want the cyclohexane, as you'll see next week with those lectures, because this goes to steroids when you talk about cyclohexanes. Which I think is really cool and fun. But, you know, apparently I'm sadistic. Okay. With that, we're at time. So if you've got questions, you can come talk to me after class. We've got lab coming up here in a second, all that fun stuff.